Good morning, everyone. Thank you for being here today. It's a pleasure to be at this podium representing our Center for Geotechnical Modeling at UC Davis. I'm going to draw some commonalities between my presentation and the ones right before, because there are a lot of common points to make. The other point I want to bring up is that with the exception of a project that is currently running, our centrifuge facility has not made an appearance in Pier for more than 10 years. So my presentation is going to focus on some broader aspects of our facility, its capabilities, and accessibility to it. So my goals for today are to discuss some of the value of hypergravity experiments. I'm going to be defining what that is, showcase some of the capabilities of our facility, and then wrap up with some short examples and options for its use. So I'm going to take a very broad step back and just emphasize the fact that in engineering and in science, we are developing our models and our tools based on observations. Those can come from the field, but more often than not, especially for civil engineering infrastructure, those may come from experimentation. And that has to do with the fact that our infrastructure is very diverse. It can span very different systems, lots of configurations. We have very rare and stochastic events. Instrumentation can be really expensive, so we don't have the luxury to always wait for these events to happen in instrumented systems. So we typically go to the lab, big or small. Our lab, I'm going to show that in some of the later slides, but the idea is the same. We have a field problem that is challenged with certain issues, and the overarching purpose of hypergravity experimentation is to enable us to expand the range of conditions in a more simplified configuration, and then draw conclusions, understand the mechanics, inform simulations, this has been mentioned before, and upscale back to the field. So progressively in the slide, I'm going to go from the field problem. This is typically simplified in a problem first in 1G that is emphasizing the mechanisms of interest, and then with hypergravity experimentation, you reduce that subject to scaling laws to the scaled model. The scale model is in turn subjected to a broad range of loading paths and conditions such that we can draw conclusions on the mechanics that are governing that system. We're scaling back to the simplified problem so that we can draw conclusions about the mechanics. Then typically validation is performed at the 1G scale just so that you have a nice touch with reality. But if some of the scaling laws can cause confusion, I'm not going to go into the details of that. Simulations can take place in the reduced scale model and have a direct one-to-one comparison with what was observed in the experiment. Having understood all the mechanics and having developed confidence in your tools through the validation, you can then generalize the field and examine more conditions. And this is not unsimilar to what we have heard so far. So the 2 points for scaled modeling is that we can understand fundamental processes and we can have a basis for validating theoretical and computational models. I'm showing some pictures here from an old project which was comparing a mediated with wick drains liquefiable slope and a liquefiable slope with no mitigations, and seeing how the wick drains can assist in the dissipation of pore pressures and through that reduce the observed displacements. Those were later paired with 2D finite difference simulations that were validated against the tests and then expanded to more conditions. This is an exercise that keeps happening more again and again. In this example, and on the right, I'm showing a DSM 3D grid in the centrifuge in the 3D rendering, some of the excavated views of the DSM grid, and then 3D simulations. Just to bring everyone on the same page, I'm now going to bring the Center for Geotechnical Modeling and the principles of hypergravity testing into this slide, which comes to resolve the need to mimic the gravity conditions that are particularly important for the behavior of soils. So this is a cartoon of our 9-meter radius arm. This is going to spin around its center axis. It has a 9-meter radius eventually. when you reach about 75 G in centrifugal acceleration or 90 RPMs, the box will raise around that pivot point, and inside you can have the model resting on a shaking table. It is a 1D actuator, so we can apply motions up and down in the slide as you see it right now. And the principle is that the centrifugal force is that hypergravity that is making up for your smaller model and bringing in the overburn that is so important for all soil structure systems. Now, this arm is housed right here where you see the 9-meter centrifuge rotunda. The Center for Geotechnical Modeling occupies 3 different buildings. In this building, we have the control room and everything that has to do with instrumentation and calibration and electronics. And in here, we have the 9-meter prep room where the models are built and then transferred down here into the rotunda. But also here, we have the 1-meter centrifuge, the Shavits, which is also there to assist with plenty of research questions. Our operational vision is to provide open and equal shared use access. We're operating currently under the NERI award. I have 2 pictures here of our large centrifuge and our smaller one. We aim to enable major advances to predict and improve the performance of soil and soil structure systems, and we're constantly onboarding infrastructure and methods for new science. We haven't done any major upgrades, but we consider that every centrifuge test we do brings a new component and capabilities into our system. A picture of our leadership and staff. Our new director is sitting right there, so you can ask them all the hard questions. We also have Dan Wilson, who's our associate director, 2 faculty advisors, and then our past directors are always involved and happy to chat about the facility. And our operations would not be possible without Tom, Chad, Anatoly, and Carissa. And we will be soon opening up a position for a business operations manager, dabbling between research and managing. So keep your eyes open for that if you're interested in participating in our facility. Some of the goals and objectives we have, I find them to be very near and dear to what PEER is also seeking to provide to the engineering community, but also society overall. And we're always looking to extend the breadth and diversity of our user base, which is one of the reasons we're here today. Some details on the 9-meter centrifuge. It's unique in the world. It's the largest radius equipped with a shaking table. It can test soil boxes that have at least 1,500 kilograms of soils. And the benefit here is that you can fit a holistic system into it, leveraging the scaling laws, and you can play with various stratigraphy, structural configurations, and explore many, many systems in that space. You can afford to have very dense instrumentation inside that box, from pore pressure transducers, accelerometers, LVDTs. We have developed new methods for tracking displacements through cameras, and also you can perform in-flight soil characterization to provide lots of resolution in what you have in your container, in your soil, both before shaking, for example, and after. Lots of the operations on the 9-meter centrifuge are supplemented and enabled by tests on the 1-meter centrifuge. I'm showing here a picture. It's a close-up view where we were looking at bioremediation of liquefying sands, and now this type of testing has been upscaled to the 9-meter centrifuge enabled by the testing here. It has the exact same data acquisition system, just you have an order of magnitude less instruments, but the point here is that we do not have to maintain unique sensor inventories. You can do efficient exploration and some rapid parametric tests. It's much faster and cheaper to do tests on the 1-meter centrifuge, and through that you can increase the quality and complexity of the subsequent 9-meter tests. Since we have seen some shake table tests or shake tables already, this is an older view of the San Diego shake table facility, just to bring a view of what you can afford. I didn't hear details about how much soil you can get in there. You can get probably, here it was 3 meters, but I think you can go further than that. But the point is that in our facility, you can have hundreds of meters of soil represented. So if that's of interest to the test, the centrifuge is there to help. What are some common traits for successful projects? It always has to do with starting from what you want to study. What is the mechanism you're trying to resolve? What system behavior do you have your eyes on? And this has to be articulated through deciding, do you want to validate numerical simulations? Do you want to validate design methodologies or revisit them? Or do you want to simply identify mechanisms and behaviors to do later inverse analysis through those? Ultimately, the model that is designed has to be emphasizing the mechanisms. It has to be simple, not too simple, to bring out the mechanisms of importance. I'm going to show this a little bit later, but this is a cartoon cross-section of a project we wrapped up a couple of years ago with Bruce Cutter and our former student Sumit, funded through Caltrans. And the project there was targeting to track down drag on piles as imposed through the reconsolidation of liquefiable layers. And as you can see, we have a simple layering. We have a thick layer of loose sand. We wanted that layer to liquefy and bring out all the reconsolidation it could do afterwards. And then our piles were heavily instrumented internally so that they can track all the behavior across their length. And then the free field was also heavily instrumented to track at every depth what was happening in terms of pore pressures and accelerations. How can you have access to the centrifuge? As you stand right now, you all have access to it. All of us are always available to chat. We have a mentors program. You can see a long list of names who are great past users and current users of our facility, and all of them have pledged they're available to help and guide you through the process. All of our reports and data are available on the CGM website and increasingly now on NERI Design Safe. And the goal there is for you to find reports that are very, very carefully documenting every part of a test so that you can learn from it before you start thinking about your own tests. We have sample data and codes there to enable processing and getting, some hands-on idea of what you expect to get from the test. The facility, as I showed it, it enables to have some parallel workflows so that we can maximize the usability in there. And because students are ultimately doing the work, we have established ladder mentoring practices whereby we try to partner students. The recharge rates also reflect that. We encourage teams to be partnering up and mentoring each other so that the students increasingly become capable of leading the test that is later coming down the line. We are advancing our onboarding procedures, and most importantly, we offer customization. So the CGM supports its users in developing, commissioning, and using new experimental techniques that are always in the forefront of the field of physical modeling. So no experiment we ever see is similar to the previous ones, and there's always a different need, whether that's in the protocols you follow, in the equipment you need, in the instrumentation you need, and the monitoring you're gonna do. 3 examples that I have, but there's plenty. Every test has had something new come to it. I mentioned it before. We have developed a method for doing 3D stirphotogrammetry with the TIMA software and some high-speed cameras. That now has been established and it's used and has been used by at least 2 more teams at the centrifuge. We have had customized boxes. This is an example from our colleague Alejandro Martinez and his project from EPRI on runout behavior of impoundments. This is the tsunami tank developed back in the day from Bruce Cutter, Lars Peterson for a project out of Oregon State University. And this is just to name a few. A point on technology transfer, which is important for peer. We have seen great success, and it's a goal if you want to have impact to do technology transfer. We have seen that this is quite successful when you partner early on with interested stakeholders or early adopters on the research team or targeting to resolve a current concern in practice. And we have seen impacts on documents by Caltrans and other professional society committees. I'm going to show 2 examples, and these are projects I have been involved in because that feels more comfortable to talk about. This is a project funded from NSF, so the rates were really, really low. Under those operations, the cost for NSF funded projects is minimal. That was a test aiming at studying soil structure, water interaction effects, and buried storage tanks, and we did it in 2 phases. The first phase was a very simple box that I'm showing here. That was a new rigid box that we mounted on a new strong floor that we have, so it's smaller than the typical laminar boxes that we have there. The strong floor and the combination with smaller boxes allows for quicker tests and mounting different configurations. So this is how it shows on the arm, and we filled it up with water at different elevations. We instrumented it internally, and we basically excited hydrodynamic loading to understand what we can afford in terms of scaling and sizing inside the arm. In the second phase of this test, we came closer to reality. We aimed to represent some of the most recent constructions of buried storage tanks. I'm showing here the Headworks East Reservoir in LA. I'm showing here a simple cartoon from how it looked down in our centrifuge. The instrumented model tank placed inside the container before being buried, and then we performed 3D numerical simulations to validate the test and then expand in other configurations. So that was from NSF. This was a project I showed before, funded from Caltrans. Also 2 series of centrifuge tests. The one I showed before had a simple profiling. Then we moved out to something more complex, having established that we can measure the types of responses we were interested in. This is a configuration with the cameras that I showed earlier and some of the excavation points where we observed at Sand Bowl afterwards. Everything has its price, it has mentioned before. There are ways to get a lot of mileage from the centrifuge. So I want to say again, it's free, it's open for use by all. Our recharge rates are published on our website, and you can find lots of the details as they pertain to the facility. The recharge rates are from 2015. We're looking to update them, so stay tuned for that. If you have an NSF project, Jason is going to talk about one such example later. You can use peer funding to, say, cover students, because the tests can be covered through NSF. Those are different things you can do there. CGM is there to provide guidance, training, and support for our diverse user base. We have a workshop on the 12th and 13th of October. The call has been emailed and posted, I think, on the NERI Design Safe website. You can attend in person or online, and we'll be very happy to see you there and chat today or any other time about exploring possibilities. With that, I want to thank you and welcome any questions.